Hi, I'm Ken.
And I'm Nick.
We're here with 8 Steps to Success, and today we're going to show you the 8 steps to curve sketching. Here are the 8 steps to curve sketching. Step 1, find the domain of your equation. Step 2, find the x and y intercepts. Step 3, check for symmetry, both even and odd. Step 4, find your asymptotes.
Step 5 is find the intervals of increase and decrease for your function. Step 6 is the maximum and minimum values, both local and absolute. 7 is the concavity, which way is it orientated. And 8, the final step, sketch your curve. So it's Nick here, and I'm going to be showing you how to find the domain of our function x to the power of 5 over x squared plus 3x plus 2. And if you want lessons on how to find the domain, click here. So we take the bottom part of our function, x squared plus 3x plus 2, and set it equal to 0. Factor this, x plus 2, x plus 1. And we know that the non-permissible values of our function are -2 and -1, which indicates that there could be asymptotes at these locations. That was how you find the domain of our function. So it's Nick again. I'm going to be showing you how to find the intercepts of a function. And if you need help remembering how to do this, you can click here and it'll take you to a quick review video on how to do it. So let's get started. So to find the y-intercept, that is when the x-coordinates are equal to 0. So you just plug in 0 for everything. And we find that it's 0 over 2, which is equal to 0. Simple enough. And then for the x-intercept, and we plug in 0 for the y value, and we leave the x values as they are. And then we cross multiply this over, and this crosses out, and we get 0 is equal to x to the power of 5. And if you take the 5th root of 0, it is still 0. So x is equal to 0. And that is our y-intercept for our function x to the power of 5 over x squared plus 3x. Okay, so now we're going to be finding the symmetry of our function. And if you need a quick reminder on how to find the symmetry, you can go ahead and click here, and you'll be taken to a quick little review video. So f of x equals f of negative x. And then we set our function, x to the power of 5 over x squared plus 3x plus 2 equals negative x to the power of 5 over negative x squared plus 3 times negative x plus 2. And we know that negative x to the power of 5 will remain, x squared will become positive, and it'll become minus 3x plus 2, and that these are not equal, so this represents that this function is not even. And on to the next check, which is f of x equals negative f of negative x. So we just write out our function again. And we plug in this. Remember to put a negative sign in front of the brackets. Oh, it's the power of 5. Wait, what's the plus? Plus 3 times negative x plus 2. And you find that x squared, or x to the power of 5 rather, over positive x squared minus 3x plus 2 is not equal to the original function, so therefore this function has no symmetry and is not even or odd. Show you how to find the asymptotes of a function, or of our function, sorry. And if you need a review on how to do that, you can go ahead and click here and it'll show you. So first, remember that the restrictions were -2 and -1 as found in the very first step. So if we take the limit of f of x as x approaches -2 from the right side of x fifth over x squared plus 3x plus 2, that means we have to plug in a number to the right side of 2, which in this case would be like -1.99. So -1.99 over 5 all over -1.99 squared plus 3 times -1.99 plus 2. That means you get a negative number over a positive number, which indicates that this has an asymptote approaching -infinity. So now we have to take the limit of -2 from the other side. So we go limit f of x, our function, as x approaches -2 from the left side, and we plug in -2.01 to the power of 5 over -2.01 squared plus 3 times -2.01 plus 2. And when we simplify this, we'll get a negative number over another negative number, which indicates that we have our asymptote is approaching positive infinity. So we have just correctly proven that there's an asymptote at -2. So now we're going to check the asymptotes or check the limits for -1. And to do this, we're going to approach -1 from the right-hand side. So -0.99, let's say, power of 5, over -0.99 squared, plus 3 times -0.99, plus 2. And when you simplify this guy out, you'll get a negative number over a positive number, which indicates that it's approaching -infinity, which half proves that there's an asymptote. And if we approach -1 from the left side, we have to plug in a number that's close to -1, but just a little bit below it. So -1.01, let's say, to the power of 5, all over -1.01 squared, plus 3 times -1.01, plus 2. So then when we simplify this guy out, we'll get a negative number over top of another negative number, which indicates that our function is approaching positive infinity when it's getting closer to -1 from the right-hand side. This math proves that there's also an asymptote at x equals -1 for our function. So now that we've proved the existence of our two vertical asymptotes, we can take this time to try and prove that there's a horizontal asymptote. And a horizontal asymptote is when the limit of f of x is approaching an infinity, whether it be positive or negative. So then we take our function, and we divide it by the highest power of x on the bottom. So we do x to the power of 5 over x squared, all over x squared over x squared, plus 3x over x squared, plus 2 over x squared. And then we plug in infinity. Or we can simplify first, actually. So we get x to the power of 3 over 1 plus 3 over x plus 2 over x squared. And we can sub in infinity. So we get infinity over 1, because these two fractions simplify to 0 as 3 over any number, or 3 over infinity is equal to 0, and 2 over infinity squared is also equal to 0. So 1 plus 0 is still 1. And then we have just proved that there is no horizontal asymptote ever. And then we have to prove that it never approaches negative infinity. So we do the exact same steps as before, except approaching negative infinity. And I'm going to go ahead and skip to here, where we've already simplified our function. So we have x cubed over 1 plus 3 over we sub in our negative infinity. So we have negative infinity over 1 plus 0, because yet again these cancel out, or they just become negligible in the equation. So then our answer is just negative infinity, which coincides with this to prove that there's never a horizontal asymptote on our equation. So no y.
So now that we've found our asymptotes, we're going to be checking for the intervals of increase and decrease on our graph. And to do that, we're going to need to take the derivative of our original function right here. If you need a review on derivatives, click right here and go to the review video. So, to start, we rewrite the function y equals x to the 5 times x squared plus 3x plus 2 to the negative 1. Here we apply the product rule to attain y prime equals 5x to the 4 times x squared plus 3x plus 2 to the negative 1 minus x to the 5 times the derivative of our inside function, 2x plus 3 times x squared plus 3x plus 2 to the negative 2. Next we expand our bracket. 5x to the 4 times x squared plus 3x plus 2 to the negative 1 minus x to the 5 times the derivative of our inside function, 2x plus 3 times x squared plus 3x plus 2 to the negative 2. We expand. Next we have to attain a common denominator. In this case it will be x squared plus 3x plus 2 all to the negative 2. So we must multiply 5x to the 4 by x squared plus 3x plus 2. Our next part remains the same. Negative x5 times 2x plus 3. And this is now all over x squared plus 3x plus 2 squared. Our next step is to expand the brackets. And we get 5x6 plus 15 x to the 5 plus 10 x to the 4 minus 2x to the 6 minus 3x to the 5. And that remains over x squared plus 3x plus 2 squared. We now collect like terms and simplify our equation down to 3x to the 6 plus 12x to the 5 plus 10x to the 4 over x squared plus 3x plus 2 squared. This final equation is the derivative of our original. Now that we've found our derivative, the next step to finding the intervals of increase and decrease on our graph is to find the critical points of this new equation. To do this, we set the derivative of y prime, equal to 0, and solve for x. To solve for our variable, we can cross-multiply to eliminate the fraction, leaving us with the equation 0 equals 3x to the 6 plus 12x to the 5 plus 10x to the 4. This equation factors to give us 0 equals x to the 4 times 3x squared plus 12x plus 10. Now, to find our critical points, we have to use the zero value theorem. And to do so, we must first factor this section of our equation. Because it does not factor traditionally, we use the quadratic formula. Because this does not factor normally, we must use the quadratic formula, which gives us the equation x equals negative 12 plus or minus root 144 minus 4 times 3 times 10 all over 6. This simplifies to x equals negative 12 plus or minus root 22 over 6. This gives us two of our critical points, and the final one, of course, is x equals 0 as the final section of our equation.
We're good. Yeah.
Now that we found our critical points of x equals negative 12 minus root 22 over 6, root 22 minus 12 over 6, and 0, we put these values on a number line. We can now test the intervals of increase and decrease between each of these points by plugging in values into our derivative. First, let's try negative 3. We plug in negative 3 for our x values. From here, we simplify and expand our brackets to determine that f prime of negative 3 is equal to 81 over 4. Because this is a positive number, we say that all x values less than negative 12 minus 22 over 6 are increasing, because the derivative is greater than 0. Okay, one down. Next, we test a point between our two critical points. Take, for example, negative 2.5. We plug that value into our derivative and take f prime of negative 2.5. We set negative 2.5 into all of our x values, as we did with negative 3 before. We simplify this equation and determine that f prime of negative 2.5 is equal to negative 86 and 29 over 36. This means that between our critical points of negative 12 minus 22 over 6 and negative 12 plus root 22 over 6, our graph is decreasing because the derivative is negative. We can now check for our third interval of increase or decrease by plugging in a value between our critical points. Take, for example, negative 1.1. We put this value into our y prime equation. And we simplify this equation to attain 18 and 61 over 810. Because this value is positive, we know that our graph is increasing between those two critical points. To determine our final interval of increase or decrease, we plug in a value greater than 0, our largest critical point. Take, for example, 1. We put this value into the equation of the derivative. We then simplify this equation to attain 25 over 36. Once again, because this value is positive, we know that our graph is increasing at all x values greater than 0. So, looking at our number line, we now know that on the interval of negative infinity to our first critical point of negative 12 minus root 22 over 6 is increasing because its derivative is positive, as is our graph between negative 12 plus root 22 over 6 to 0, at which point the derivative is 0, so it is neither increasing nor decreasing. And then finally, on the interval of 0 to infinity, which means that our graph is decreasing only between negative 12 minus root 22 over 6 and negative 12 plus root 22 over 6. And those are our final intervals of increase and decrease. Now that we know our intervals of increase and decrease, we can determine where we will locate a local maximum and a local minimum on our graph. So, looking at our critical points on the number line, you can see here that until the point negative 12 minus root 22 over 6, our graph is increasing. And after that point, it is decreasing. Therefore, we know that this point is a local maximum on our graph. On the other hand, this point, negative 12 plus root 22 over 6, the graph leading up to it is decreasing, and after that point, the graph increases. Therefore, we know that point is a local minimum. Finally, our third critical point of x equals 0, because the graph is increasing on either side of this critical point, we know that it is neither a maximum nor a minimum and must be a saddle point. Okay. Now that we know that a local maximum will be located at our first critical point, we can plug in our x value of negative 12 minus root 22 over 6 into the original equation to solve for the y value at that point and determine our local maximum. This has already been done for me, as you see here. So we simplify this equation to obtain y equals negative 119.5. Therefore, our graph has a local maximum at the point negative 12 minus root 22 over 6 and negative 19.5. Now that we've determined the value at our local maximum, we can now check our second critical point, which we've determined to be a local minimum, and determine its y value. So yet again, we plug in our critical point into our original equation, and this simplifies to y equals
15.5.
This equation simplifies to y equals 15.5. Therefore, we know that we have a local minimum located at root 22 minus 12 over 6 and 15.5. Actually, give me a sec. I'm just going to think this through. So, using our critical points that were placed on the number line just here, we determined that our graph has both a local maximum and a local minimum. Welcome to step 7 of curve sketching, concavity. In this step, we have to determine intervals where concavity is facing up and where it is down. To do this, we take the second derivative of our equation, as is shown here, and we get y double prime is equal to 2x cubed times 3x to the 4 plus 24x cubed plus 72x squared plus 90x plus 40 all over x squared plus 3x plus 2 all to the 3. We set this equation equal to 0 and also find its non-permissible values, and this determines our points of inflection or saddle points. In this case, those points turn out to be y . In this case, our points turn out to be x equals negative 2, negative 1, and 0. These values are obtained by setting the derivative equal to 0, which gives us the x equals 0 value, and its non-permissible values of x cannot equal negative 1 or negative 2. Now that we've found our points of inflection at x equals negative 2, negative 1, and 0, we put these values on a number line and test values between each of the points. We start by taking a value below negative 2, in this case negative 3, and plugging it into our y double prime equation, derivative equation, as shown here. Once expanded, this will yield a negative number. What this means is that for all x values less than negative 2, our equation is concave down, meaning it opens downward. Next, we'll try f prime of negative 1.5. This value, when plugged into our second derivative equation, yields a positive number, which means that for all values between x equals negative 1 and negative 2, our equation is concave up. So because at the value below negative 2, our concavity was down, we can say that for all values under 2, the concavity of our equation will be negative. Next, we look at the interval between negative 2 and negative 1, which is positive. Therefore, it is concave up on that interval. Thirdly, we look at the interval between negative 1 and 0, which was once again negative. Therefore, you can say that on that interval, our equation is concave down. And lastly, we look at an interval above 0. Take, for example, the f prime of 1, which was a positive number. Therefore, for all values greater than 0, our equation is concave up. And here are our intervals of concavity. Here we've written down all of the information gathered in our first 7 steps of curve sketching. We've included asymptotes, intercepts, symmetry, our intervals of increase and decrease, our local maximums and minimums, and our concavity. And now we've made it to our 8th and final step, sketching the curve. Nick?
So here's what our function looks like, and we've gathered all this information here and applied it to our graph of f of x. And here's our y-intercept, for example, at 0, 0. We have our asymptotes at -1 and -2, a local maximum negative 119 on the y-axis, and a local minimum at 15.5. None of our lines cross the asymptotes at any point, and that is what our graph looks like for the function x to the power of 5 over x squared plus 3x plus 2.
Thanks for watching. Tune in next week for more of 8 Steps to Success with Nick and Ken. Nice. Okay. Cut and print.